Please join me in welcoming to the Distinctive Voices podium, Dr. Chris Rorres.
Okay, hopefully you can hear me okay, and hopefully my little pointer is working. And let me get on the right slide. This is it. This is the title of my talk, and you can see that it has the word "and" in it, which means it's going to be split into two halves. The first half basically will be on Archimedes, and the second half will be on what he contributed to the quest for the theory of everything and where that quest remains today. So let me begin first with Archimedes. Here are some images of Archimedes. You'll see a lot of postage stamps in this talk, my philosophy being that only important people get their pictures on postage stamps, so I'll only be talking about important people tonight. The four images on the right are all based on this sculpture that is in the Naples Museum, Naples, Italy, that is, Archaeological Museum. Unfortunately, it's not a statue of Archimedes. It is a statue of Archidamus. And if you look at the description here, Archidamus was a 4th century king of Sparta. Apparently, someone got the name Archimedes and Archidamus confused. It got to the photo agencies, and now anytime anybody asks for an image of Archimedes, they give them this erroneous image. In fact, no likeness of Archimedes has survived. And this is typical that we have the likeness of kings, but not of mathematicians. In fact, let me quote you this thing that Martin Gardner wrote. Biographical history, let me read from here. Biographical history, as taught in our public schools, is still largely a history of boneheads. Ridiculous kings and queens, paranoid political leaders, compulsive voyagers, ignorant generals, the flotsam and jetsam of historical currents. Those who radically altered history, the great scientists and mathematicians, are seldom mentioned, if at all. This, Martin Gardner is one of my heroes, incidentally. The picture that you see here is from yesterday's New York Times. They had a story on him because today, October 21st, is his 95th birthday. And he celebrated it by issuing his second book this year. In fact, he has published over 70 books, one of them, of course, being on Archimedes. Archimedes, a mathematician and inventor. So let me first say something about Archimedes, the inventor. Then, as a mathematician, I'll switch over to Archimedes as a mathematician. Probably the best known invention of Archimedes is the Archimedes screw. This is a device that dates from the 3rd century BC. Archimedes himself did not write anything about the Archimedes screw. In fact, he didn't write anything about any of the war machines and inventions credited to him. Only his mathematical writings survive. But by other authors, we know that he did many things besides those mathematical writings that survive today. This is a fresco that you will find that is located also in the Naples Archaeological Museum. Unfortunately, it's not on display because it is part of a larger erotic fresco. So it is located in some back room someplace. You have to ask the guard if you want to see this. This was mentioned that I appeared on a few documentaries. This is one that Terry Jones of the Monty Python group put together a couple of years ago. He now does documentaries. He invited me to come and talk about Archimedes, and of course he didn't want to hear anything about Archimedes' mathematics. He wanted to hear about his inventions and his war machines. So here I am demonstrating the Archimedes screw by stealing some beer from his glass. This was in Syracuse, Sicily, where Archimedes lived his entire life in the 3rd century BC. I am also particularly interested in the Archimedes screw and coming over here to Los Angeles because, in fact, the largest installation of Archimedes screws in the Western world is just about 40 miles northwest from here at the Hyperion wastewater treatment plant. There are 10 huge screws here that lift water, wastewater, as it comes in, and then it flows under gravity through the rest of the plant. And the Archimedes screws are ideally suited for this kind of wastewater treatment. They can handle dirty water, debris-laden water very well. They're a very robust instrument. And incidentally, since I came from Philadelphia, incidentally, don't blame me if the Phillies win tonight, but since they're playing even as we talk. Since I have this opportunity to be in Los Angeles, I'll be giving a talk also at the Hyperion wastewater plant on Friday at 1:30. I'll be talking specifically about Archimedes screws, their history and their use, and some research that I did on the optimal design on the Archimedes screw. So if any of you want to come at 12:30, you have to call first, but you're all welcome to come. Okay. Besides the Archimedes screw, most of his other inventions are associated with his title as the chief military engineer of Syracuse, Sicily. He was a relative of the king of Syracuse at that time, King Hiero, and Syracuse is located right here on the eastern coast of Sicily. The white outline here you see are the defensive walls of Syracuse. While he lived there in the 3rd century BC, Syracuse was one of the most important Greek city-states in the Mediterranean. Of course, it was in the Mediterranean. All the Greek city-states are in the Mediterranean. Together with Alexandria and Athens, Syracuse was a center of learning. It had been founded some 500 years earlier, and it was at the height of its glory in the 3rd century BC. But in the year 213 BC, it was under attack by the Romans. And Archimedes, here he is planning the defenses of Syracuse, had a significant amount of military experience and designed the fortifications of Syracuse at that time. But in 213 BC, the Romans attacked, and here are some posters from an Italian movie entitled The Siege of Syracuse. These are in 3 different languages. The story itself has who is it now? Rossano Brazzi as playing Archimedes. The story is absolutely ridiculous, but at least the Italians were interested in the Siege of Syracuse, and at least they got this little map right. Rome is up here on the mainland, Carthage is on the northern coast of Africa, and Syracuse is right between the two. And since the Punic Wars were between Rome and Carthage, the Greeks in the Greek city-state of Syracuse got drawn into it. First, they allied themselves with the Carthaginians. Then, when King Hiero died, they switched their allegiance to the Romans. Right? No, I got that backwards. They started out allied with Rome, then they switched their allegiance to the Carthaginians, whereupon Rome attacked in 213 BC. But Archimedes was ready for them with his military machines. This was the layout of Syracuse at the time. This is the defensive wall of Syracuse. The Romans attacked from the sea and by land. And on the sea, there were 60 quinqueremes. These were the battleships at the time. And these 60 quinqueremes were attacking the walls of Syracuse. And these little circles that you see here represent the location of these military machines, these Archimedes claws, as they are now called, also called iron hands. And as you can see, as a Roman ship attempted to come and scale the walls, a grappling hook would grab it and then lift it and then drop it into the sea. And in this way, Archimedes was able to fend off this siege by the ships. This model that you see here was for another documentary that I appeared in called Archimedes' Claw. This was in 1999, something the BBC put together. Together with a structural engineer, Harry Harris, we did this stop-action little movie that shows the operation. But this little movie also shows two things that I'll be talking about today. Two of the basic physical laws that Archimedes formulated and proved and discussed. One of them was the law of the lever. The machine itself, the claw, is basically a huge lever. It has a grappling hook at one end and a leaden counterweight at the other. And when the grappling hook attaches itself, to a ship, the leaden counterweight is swung back, the ship is jerked up, and then it is caught off balance and tips over. The law of the lever, Archimedes' law of the lever, is demonstrated by the iron hand itself. And the other law that Archimedes is credited with is the law of buoyancy. And here you have the law of buoyancy and the stability of floating objects in operation as you destabilize the ship. So you have the two fundamental laws of nature that are credited to Archimedes. He formulated these laws, he proved them geometrically, and then he applied them to military machines. He was an entire vertical industry. He did everything himself, from the theory to the actual construction of the machines. They were very effective. The Romans had never seen anything like this, and they called off their siege of Syracuse. Instead, they blockaded the city, and unfortunately, after a long blockade, they were able to take advantage of the Syracusans' neglect of their defenses, scale the walls, and then capture the entire city. And thereafter, it was a minor Roman provincial town. For 500 years, it was this glorious Greek city-state, and now it just went into oblivion. I can't end this story without telling you what happened to Archimedes. This is a legend, probably untrue, that he was killed in the siege of, that he was killed in the siege of Syracuse is known. But the legend is that at the time he was killed, he was working at his desk on some problem. The Roman soldiers who had captured the city were given 1 day's leave to sack the city. This was their payment. They all expected that. So for 1 day, they went in and grabbed everything they could. A soldier came into Archimedes' workshop to see what was there to steal. Archimedes was disturbed by this, and he shouted, "Don't disturb my circles." And with that, the soldier slew him. The story is a little too good to be true, but it is on record that he was indeed killed in the siege of Syracuse. Many authors attest to that fact. But who would have recorded this, for example? It's hard to say. I doubt that the soldier himself would have quoted that. But going back to Archimedes now and his inventions, as I mentioned, he is mainly known through his works, his writing works. None of his inventions actually survived intact, at least in his lifetime. But these 9 works of his survive. And even if no legends about him survive, these works were enough to proclaim him the greatest mathematician of antiquity. 9 works, all of them, except for these 2, are purely geometrical works having to do with finding the volumes of solids, finding areas, arc lengths, tangent lines, the things that are the basis of modern-day calculus. In fact, Archimedes is sometimes called the father of integral calculus, one of his titles. But we'll be interested mainly in his other title, which is the father of mathematical physics. He was the first to really, in a hardcore way, apply mathematics to physics. And in these 2 works, on the equilibriums of planes 1 and 2 and on floating bodies 1 and 2, he took the 2 fundamental laws that I talked about, the first one being the law of the lever in this work here, number 1, and the second being the law of buoyancy, number 6 here on floating bodies. And in both of these works, he discusses these two physical laws. And what he attempts to do, though, something that was not done before is put them on a strict axiomatic formulation. There were certainly physical laws discussed before Archimedes, but he attempted to imitate what he had learned in Alexandria when he studied Euclidean geometry. He may have actually been a student of Euclid himself. They were more or less one generation apart. More likely, he studied under the students of Euclid. And in doing so, he studied the axiomatic system. Now, I realize there are too many words on this slide. I don't expect you to study them. I just want you to see that Euclidean geometry, if you've ever studied it, is the archetypical example of an axiomatic system. Many mathematicians, the more conservative ones, think that mathematics really began with Euclid's Elements, the idea of setting up an axiomatic system, a few basic laws, and then through deduction proving everything else in that way. Euclid did this with geometry. He started with these 5 axioms. The word axiom is a Greek word, axioma, which simply means something that is worthy, a worthy thing. So Euclid tried to come up with the most basic, fundamental laws of geometry, sometimes called self-evident truths that no one could argue with, and then show that more complicated things like the Pythagorean theorem all followed it from these very fundamental laws, which are now called axioms. For example, any 2 points can be joined by a straight line. This is to be accepted as something absolutely true. And the other axioms are more or less as obvious as that. And starting with these very obvious statements about geometric things, you can then prove more complicated things like the Pythagorean theorem, which is not obvious, which is not a self-evident truth, which is something, though, which will follow from these 5 axioms. Now, Archimedes attempted to imitate this style in dealing with physical laws. And this is what really I'll be talking about today, and showing how his law of the lever and the law of buoyancy are based on an axiomatic system, which ultimately led to the idea of coming up with the axioms of the universe, of a theory of everything. So let me first discuss the law of the lever. It seems that there's a legend about Archimedes associated with everything he ever did. And on the law of the lever, he is credited with this statement here, "Vas mi pustake kinotin," which in English means, "Give me a place to stand and I will move the earth," as this illustration indicates. This is the basic law, the basic idea behind a lever. Given a long enough lever, you can lift as heavy a weight as you possibly can imagine. And here is Archimedes, the fulcrum here in the middle, the earth at one end, and Archimedes pushing down on the other to lift the earth. The king of Syracuse, as I mentioned, King Hiero, asked him to give him a demonstration of this fact. And again, according to legend, Archimedes used his lever to launch a ship which was waiting to be launched. And all by himself, he was able with a lever to launch this huge ship. And Hiero was so impressed by this that he issued the decree that from this day forth we must believe everything that Archimedes says. A decree that is still in force today, in fact. Now, though this is the legend, this is the fact, this is one of the 9 Archimedes works that survives, entitled On the Equilibrium of Planes. And again, by no means do I mean for you to read this. I just want you to see the flow of the work here. He begins with the following. I postulate the following. A postulate is the same as an axiom. What he is doing is listing 7 axioms that he regards as self-evident truths, something that everybody can accept. And he lists them here. I'm sorry, did I go? Here we go. I postulate the following. Equal weights at equal distances are in equilibrium. That's axiom 1, act 2, 3, 4, 5, 6, 7. These are the self-evident truths, the axioms that he begins with, none of which have anything to do directly with the law of the lever. And after he finishes states the 7 axioms, he begins with proposition 1. Propositions are exactly the same as theorems, so we have the axioms on the left followed by the theorems. This is the way, unfortunately, mathematical papers still are written today. A statement of your assumptions, and then you immediately start proving what you want to prove. No motivation, no discussion, no elaboration, just the facts. Not a single iota more than you need to. So he doesn't even say, I now prove the following. He immediately starts proving things. He states what he's going to prove in italics, then proves it. And after the proof, he starts with proposition 2, states it, proves it, and so forth down the line. Eventually, he comes up with proposition, pushing the wrong button here. All right. I seem to be missing a slide here. Oh, okay. Eventually, he proves in proposition 6 and 7, which you cannot see here. Basically, they are a statement of the law of the lever, and that's what the next slide shows. The law of this lever has its own postage stamp, in fact. The 10 formulas that changed the face of the Earth, and here it is, the law of Archimedes, F1, X1 equals F2, X2, which means the following. If you have two weights of weights F1 and F2 at the end of the balance, and they are of distances x1 and x2 respectively from the fulcrum, then the ratio of the two forces is equal to the ratio of the distances in the inverse order. A very simple law, the law of the lever. It's not that Archimedes proved what a lever was. Even chimpanzees use levers. He quantified the relationship between the forces of a lever and the ends of the distances of those forces from a lever. And this is a physical law stated in mathematical terms. Now, the second law that I mentioned relating to Archimedes' work was his law of buoyancy. And just as he did with the law of the lever, he attempted to prove this on an axiomatic basis, to first state some things that were obvious and clearly the truth, and from there prove the law of buoyancy. But first, of course, there's a legend associated with the law of buoyancy. Here is King Hiero, his supposed relative, who ruled Syracuse for more than 60 years. He lived into his 90s. And in the year 265 BC, he proclaimed himself king of Syracuse. And back in those days, the coronation of the king called for a golden crown, or a wreath in this case. This is not Hiero's wreath. This is a wreath that is in a British museum, 4th century BC, found in the Dardanelles. The legend is that King Hiero gave a goldsmith a certain quantity of gold that the goldsmith was to transform into a beautiful wreath. And when the king received the wreath, he weighed it to make sure that it weighed as much as the gold that was given to him. And it did. But then someone suggested that the goldsmith took a certain weight of gold that was given to him and replaced it by an equal weight of silver. So the crown that Hiero received was actually an alloy of gold and silver, not pure gold. And of course, Hiero was not happy with this, but he had to prove first that the crown was not pure gold. And though there were ways to do that back then, they involved in some way destroying what you were trying to analyze, or a little piece of it. Now, this was actually a holy crown because it was dedicated to the gods. The usual thing was that one of these wreaths would be, after the coronation, placed on the head of a god or goddess. So Hiero asked Archimedes to test the crown for purity, but not to disturb it in any way, to perform non-destructive testing, in other words. And the legend continues that King Hiero, as indicated here, asked Archimedes to do this. And in this illustration, let me mention something that you always see in these illustrations of Archimedes. In the year 265 BC, when Hiero was coronated, he would have been in his early 40s. And it appears to be he's in his early 40s. Archimedes, though, was some 20 years younger then Hiero. And here so he would have been in his early 20s. And he's depicted as an old man. And this is typical. Every depiction of Archimedes is as an old man with a beard and white hair. But he would have been in his early 20s if this legend were true. At any rate, the legend continues that Archimedes was taking a bath when he was studying the crown here, down here, and he felt the buoyant effect of water. He felt that his arms sort of floated, and he floated, and in this way he came up with the law of buoyancy, which I'll be describing in a moment. But this gave him a way of determining whether or not the crown was pure gold or not. Basically, to weigh the crown in air and in water, then weigh equal amounts of gold in air and in water, and then by some ratios determine the specific density of the gold. I don't have time to go into those details, but at any rate, he came up with his law of buoyancy, which allowed him to solve the golden crown problem. And he was so elated by this that he ran out of his bathtub, running through the streets, shouting, "Eureka, Eureka, I have found it, I have found it." This is the original Eureka moment. Everything, all other moments come to follow. Here he is in his workshop, and here is the mathematical work, what truly survives. This is not legend. This is a work of Archimedes in which he states and proves the law of buoyancy in exactly the same way that he stated and proved the law of the lever, and just as Euclid proved all of his geometric works. He begins with postulate 1. He doesn't even say, "I now postulate the following." He just simply says postulate 1, and then gives this rather dense postulate, which he could have easily broken up into 4 or 5 postulates, which I'm not going to read to you. Basically, the postulate is describing fluid pressure. This is the first formulation of the concept of fluid pressure, and Archimedes here described the basic properties of fluid pressure, how if you immerse a body in fluid, forces are felt all over that body. And on the basis of this one postulate, he then begins proposition 1. Again, a very methodical approach. Theorem 1 or proposition 1, statement of the proposition in italics, and then the proof. Theorem 2, statement, proof. Theorem 3, statement, proof, so forth and so forth. And finally, he gets to proposition 6, which is the first part. All right, that's interesting. There's supposed to be blue water here, and it's blue on my screen, but didn't quite make it with this projector. Anyway, proposition 6 is the first half of his law of buoyancy as it pertains to objects that float in water as opposed to sink in water. As Archimedes states, when an object such as a ship floats in water, then the weight of the water displaced by the ship is equal to the weight of the ship itself. That's why we talk about a ship's displacement. If a ship displaces 2 tons, that means it displaces 2 tons of water, and consequently it itself must weigh 2 tons. And the second half of the law of buoyancy pertains to objects that sink in water. For example, this object here, when placed in water, weighs 3 pounds less than it does in air because it displaces 3 pounds of water. So these 2 statements here constitute his law of buoyancy, one of the most fundamental laws of physics, and the basis of the entire field of hydrostatics, which is accredited to Archimedes. He is the father of hydrostatics. All right, now, so here we have these 2 laws of Archimedes that were proved by him on a very strict axiomatic basis. And now what happened then after Archimedes? I showed you one of these postage stamps. The other 9 postage stamps in that series are concerned with other laws of physics. This is a rather unusual collection of laws. I doubt if you asked 10 different, in fact 100 different physicists to come up with the 10 most important laws, none of them would come up with this particular set. But it's an interesting collection. You have E equals mc squared, Einstein's law. You have Newton's law, the inverse square law of gravity, Maxwell's laws, et cetera, et cetera. And most of these laws, though, were obtained not from an axiomatic basis, but on the basis of experimentation or observation. Most physical laws are discovered that way. Here, a better listing of scientific laws is in this book that came out last year by Clifford Pickover called Archimedes to Hawking, Laws of Science and the Great Minds Behind Them. He lists 78 laws, and the first law is one of Archimedes' two laws. This is an excerpt from his book, Archimedes' Principle of Buoyancy, which is about 250 BC, A for Archimedes, and that's the very first law that's stated. Now, that's the very first law, and then the second law out of the 78 listed is Kepler's laws of planetary motion. Now, this is interesting. 1609, we're talking about more than 18 centuries between the first law and the second law. And all the remaining laws are in the last 400 years. And this is typical that science more or less peaked in the 3rd century BC, which was the golden age of Hellenistic science, with Archimedes and Euclid and Aristarchus and Eratosthenes and other people like that. And then there is this 18th century gap where people are just waiting around for the Renaissance to begin where the 3rd century ended, and that's exactly what happens. You first had the Roman Empire coming in, where not much was done scientifically. Maybe a lot was done engineering-wise, but nothing was really done scientifically. Then following the Romans, at least in Europe, you had the Age of Faith. You had the Dark Ages, where we were all interested in how to get to heaven, not what was going on here on Earth. And only with the Renaissance, only with the 15th, 16th century did things pick up again. And that's why you have this 19th century gap between the first law and the second law in this particular book. Now, this second law here of Kepler, here he is on a postage stamp. One of his laws, he actually had 3 laws of planetary motion. One of them, the simplest one to state, is that the planets move around in elliptical orbits with the sun at one of the 2 foci. This was a law that Kepler came up with by observation. He did not prove this law or deduce it from something more fundamental. He basically took observations from his predecessor, Tycho Brahe, who spent years of his life, Brahe did, observing the location of the planets and methodically recording them. Kepler then picked up these observations on Brahe's death and showed that the only way these observations could be correct is if the planets move around in elliptical orbits. So it was not a law that was deduced from fundamental principles, from axioms. It was a law that he deduced from data. There's nothing wrong with that. And he really did try to deduce it from more fundamental laws. But you can't expect one person to do everything. Brahe collected the data, he did the data analysis, and the wisdom came from this man, Isaac Newton. Isaac Newton now has gone beyond getting his image on postage stamps. He has gone on to paper currency. If you can get on paper currency, you really made it. And certainly Newton has. He took Kepler's laws and showed that they follow from very fundamental principles that he himself formulated. And he formulated them in this work here, the Principia Mathematica, or the Principia, if you prefer the old Latin pronunciation. And in this work, which in fact has its own postage stamp, on the occasion of its 300th anniversary in 1986, this is regarded as the most important scientific work ever published, something I certainly agree with. It was just an astounding piece of research. And Newton went back to the works of Archimedes and Euclid and attempted to emulate them, which in fact he did, by coming up with an axiomatic system for classical mechanics, for what we now call classical mechanics. Here we have his axioms, axiomata in Latin, and he formulates his 3 axioms, his 3 laws of motion. To every action, there's an equal and opposite reaction. An object at rest will remain at rest, and the second law that the acceleration on an object is proportional to the force on that object. These 3 laws, which he also supplemented by his law of universal gravitation, the inverse square law concerning the attraction between any 2 particles, these were his 4 axioms from which he then proceeded theorem proof, theorem proof, theorem proof, until he was able to prove Kepler's laws of motion together with other more sophisticated laws. For example, here is theorem 30, and as you can see, he states the theorem in Latin here, and then he proves it, its statement in italics, and then the proof. Then he ends with QED, quod erat demonstratum, which is a direct translation from the Greek of Euclid and Archimedes, oper evidixe, which was to be shown. So a very strict methodical approach, theorem, proof, QED, theorem, proof, QED, until he proves Kepler's 3 laws, and also other interesting laws such as this one here. This theorem has to do with the gravitational force inside a hollow sphere, a hollow planet, for example. Newton shows that there is no force on a particle inside a hollow sphere. And this is something unusual. It's not an intuitively obvious thing that there is no force on a particle inside a hollow sphere, and there's no way that Newton could show this in a laboratory. It's a law of nature that you had to accept because it followed from his axioms. And this is something rather new in science, that you start believing things that you can't observe and that you can't really verify, but you believe them because they follow from the axioms that you do believe in. Okay, now, following Newton's Pythagorean works, there came the idea of the clockwork universe. Newton never used that phrase, but it is always credited to him, the idea that the universe is one huge, precise, and predictable machine that operates according to natural laws in absolute space and time. Predictable. In other words, if you know the axioms of the universe, you can predict the future behavior of the universe. This man, Laplace, mathematician and philosopher, formulated it this way in 1814, the beginning of the 19th century. He said the following: an intellect could condense into a single formula the movement of the greatest bodies of the universe and that of the lightest atom. For such an intellect, nothing could be uncertain, and the future, just like the past, would be present before its eyes. This intellect, sometimes now called Laplace's demon, would just grasp the entire history of the universe from the beginning to the end, just the way we might grasp, for example, an entire motion picture. We know the way it begins, we know the way it ends, and we know everything in between. This was a significant philosophical advancement as far as science is concerned. The scientists and physicists were really getting heady at that time, believing that they could accomplish everything. At the end of the 19th century, this man, James Maxwell, accomplished in electromagnetic theory what Newton was able to do in classical mechanics. Just as Newton put classical mechanics on an axiomatic basis by formulating the fundamental laws of classical mechanics, Maxwell did the same thing with the laws of electromagnetic theory and described them in terms of these 4 laws. Those 4 laws are also abbreviated in matrix form on the postage stamp here. This is the more conventional form. And this is oops, keep hitting the wrong button here. This is here we go. It's hidden back here. This is a t-shirt that you can actually buy. It's quite popular with physics majors and electrical engineering majors because it condenses their entire field into these equations. If you know these equations, you know everything about electricity and magnetism. Everything, how to aim your television antenna, is embodied in these equations. Now, with Maxwell's success in electromagnetic theory and Newton's success in classical mechanics, we were ready for the next stage. This is a mathematician, David Hilbert, probably the best-known mathematician at the turn of the century, 19th to 20th century, and who really deserves something better than a postage stamp from the Congo. But this is the best I could find. He gave the keynote address at the International Congress of Mathematicians in Paris in 1900. This is a congress that meets every 4 years. It last met in Madrid in 2006, I believe. And he, in his keynote address, listed 23 problems that enormously influenced the development of mathematics in the 20th century. If you could solve one of Hilbert's 23 problems, you became world famous, at least within a tiny community of mathematicians. And about half of them have been solved, these problems that he's formulated, and all of them have to do with something of a mathematical nature, with the exception of the sixth problem, which was simply stated as to axiomatize physics. That is, find the fundamental laws of physics by which all laws, Newton's laws of motion, Maxwell's laws of electromagnetic theory, quantum theory, relativity theory, everything should follow from these axioms. And this idea, in the first, here it is. This is the T-shirt now that we're looking for. This will be a bestseller because, the whole universe will be formulated on one little T-shirt. Now, this idea was developed in the beginning of the 20th century by Albert Einstein. In 1949, he made this statement: the supreme task of the physicist is to arrive at those universal elementary laws, that is, those most worthy laws, those axioms, from which the cosmos can be built up by pure deduction. Einstein spent the last few decades of his life looking for these axioms. They were called unified field theory in his day, and he was looking for these equations that would unify all of the basic fields of physics, electromagnetic fields, quantum mechanics, the strong and weak nuclear fields, and of course he didn't come up with them, but he was greatly interested in them and believed that in fact he could come up with them. I think it was one of the major disappointments of his life that in fact he didn't come up with them. After his death, the best known name in physics identified with this search is Stephen Hawking. In 1980, he made the following address when he was inaugurated in the location chair. This is the same chair that Isaac Newton held when he was in Cambridge. At that inauguration, he stated, "I think there is a 50-50 chance that the study of the early universe and the requirements of mathematical consistency will lead us to a complete unified theory by the end of the 20th century." So we had until 2000 to come up with the axioms of the universe, and Hawking believed it, and he actively searched for it. In the 1980s, this unified field theory, the name was sort of replaced by the theory of everything. These are some books I found on Amazon that had theory of everything on their titles. There are many more. From a PR point of view, this is a much better description than unified field theory. To say you're looking for a theory of everything, you're more likely to get funding with that than you are with unified field theory. Probably the man responsible for this particular title, Theory of Everything, was John Ellis. In 1986, I think it is. I can't see it here. He wrote a paper in Nature magazine called The Superstring Theory of Everything or of Nothing. And the title, the phrase theory of everything caught on with this paper, and thereafter unified theory was replaced by theory of everything. And this now takes us, and then what happened by the year 2000? In 1998, Hawking saw that his time was running out. No one had come up with a theory of everything, so he modified his original statement in 1980. I thought that there was a 50-50 chance of us finding a complete unified theory in the next 20 years. That is still my estimate, but the 20 years begins now. I will be back in another 20 years to tell you if we made it. So we have now till the year 2018, 9 years from now, to see if we can find a theory of everything. This takes us into the 21st century. We're 9 years into the 21st century, and some interesting developments have happened. First of all, Hawkins now wrote the following. Some people will be very disappointed if there is not an ultimate theory that can be formulated as a finite number of principles. I used to belong to that camp, but I've changed my mind. This was in 2002. Now, this is an enormous change of opinion. This is a man like Einstein, who spent decades of his life looking for a theory of everything, hoping he can find it, and now he thinks there is no theory of everything, that it's a hopeless task, that no one can find a theory of everything. Now, what happened? Why did Hawking change his mind? Well, you can get an idea from the title of his talk. This was on the centenary of Dirac's birth, Gödel and the End of Physics. The phrase end of physics refers to finding the theory of everything. It's sort of an allusion to the fact that once you found the theory of everything, physicists have nothing more to do, which is, of course, ridiculous. It's like saying because Euclid found the fundamental axioms of geometry, there was nothing more to do in geometry, when in fact many people think that the field of geometry began with Euclid, not ended with Euclid. And likewise, even if you get the theory of everything in physics, there's still plenty more to do with showing what are the consequences of that theory of everything. So that's what the end of physics means. Now, Gödel, what does Gödel mean in this title? Well, Gödel and the theorem, Gödel refers to Gödel's theorem, and Gödel is this man, Kurt Gödel, 1906 to 1978, a mathematician and logician of Austrian-German birth. And in 1931, after his doctoral thesis in 1930, he stated a theorem and proved a theorem which was monumental in the theory of mathematics, one of the true theorems in mathematics that changed the whole face of mathematics. Time magazine, when it was formulating its 100 most important personalities of the 20th century, not the most important scientists or mathematician, but just the 100 most important personalities, had on its list only one mathematician, and that was Kurt Gödel. And so if you've never heard of Kurt Gödel, you really should have, because he's one of the most 100 influential people of the 20th century. He stated this theorem, which unfortunately is a very deep theorem, and in the few minutes I have left, I'm not going to be able to do it justice. So if I make some misstatements about it, it's only because I'm trying to simplify things. But his theorem was formulated in 1931. In 1940, he came to the United States with, at the invitation of the Princeton's Institute of Advanced Study. He was a friend of Albert Einstein's, who was also at the Institute. Each man thought the other man was the most intelligent man they ever knew, and they were probably both right. And they helped each other in their respective fields, in relativity theory and in the theory of logic, which is what Gödel was interested in. You see from these two statements here, this is a kind of interesting logical paradox that you get into, which is rather curious. The statement below is false, the statement above is true. You're led into this cycle of contradiction. And most people just say that's interesting and forget about it. Gödel, though, as a logician, thought that when you're dealing with the very heart of logic, the most basic axioms of logic, something like this is important. Something like this is telling you something about the entire nature of an axiomatic system. And in his In his incompleteness theorem, I'll paraphrase what Freeman Dyson, I couldn't find the postage stamp on Freeman, it's probably too early, but I'm sure he'll get his postage stamp later. He made the following statement: Gödel's theorem implies that pure mathematics is inexhaustible. No matter how many problems we solve, there will always be other problems that cannot be solved within the existing rules. Because of Gödel's theorem, physics is inexhaustible too. Now, what is he saying here? Basically, Gödel's theorem says within any axiomatic system, there will be statements that you can make within that system which can neither be proved nor disproved with those axioms. You could then add that statement as an additional axiom, but then there will be other things you can't prove with this expanded set. And that goes on forever. That is, you can never encapsulate an axiomatic system with a finite number of axioms. There will always be additional statements that you can neither prove nor disprove. Now, because physics, at least the present way we formulate physics as mathematical statements, because physical laws are mathematical statements, the same would be true as far as any physical laws, axiomatic systems we come up for the universe. If we try to come up with a finite set of axioms, something we can put on a T-shirt, there will always be statements in physics that we can neither prove nor disprove. There will always be things we will observe in the universe that will not follow from our axioms. We then add that new thing to our axioms, and there are more things we can't prove. It goes on forever. Inexhaustible. This man, Stephen Yockey, a priest who just died this year, 2009, was also a physicist, and he made this similar statement: Gödel's theorem remains a serious assurance to all physicists that their minds will forever be challenged by ever-fresh problems. In other words, there will always be new physical phenomena that cannot be explained in terms of previous physical phenomena. The universe is infinite in its complexity, in other words. Yockey was, in fact, one of the first to see the relationship between Gödel and the theory of everything, and the title of his talk indicates that, a late awakening to Gödel in physics. Here we go back to Stephen Hawking. Here I'm zooming in on the fractal and showing that you have endless detail in this fractal, that when you think you come up with the final detail, there's always more complexity. It's kind of a metaphor from what these previous people said and what Stephen Hawking is also saying now. At the end of his speech, he said, that I previously referred to, he said, "I'm now glad that our search for understanding will never come to an end, and that we will always have the challenge of new discovery. Without it, we would stagnate." So this search for a theory of everything just was not feasible. The grapes were sour after all. There was no need to do this. The universe would be more interesting if there was not a theory of everything. Now, that attack on the theory of everything from Gödel's theorem is really an attack from below, from the axiomatic nature of a theory of everything. An attack from above concerns the problem of consciousness, which has been discussed more in the 20th century, I think, 21st century than in the previous centuries. When Laplace, for example, said that his demon could see the entire universe from beginning to end, the demon would not have been able to see human behavior. Even though Laplace regarded our physical bodies as part of the universe, our mental self, our souls were something different. These guys back then, in their time frame, thought of human behavior as something very distinct from the physical laws, that we were made in the image of God. We were not, even though our bodies are subject to physical laws, our souls were not. Today, of course, physicists have no qualms about looking at our entire entity in terms of physical laws. And that would require then some explanation of consciousness, not souls, but just consciousness. This is something we all know that we have, but no physical laws up to this time have ever addressed the question of consciousness. They have addressed the questions of brain activity and neurons and firing and all that stuff. But still, we feel there's something beyond all that because we all know we have it. We all know that we have consciousness. How do you explain it? Or if you don't want to explain it, how do you explain it away? And this is one of the problems with coming up with a theory of everything. Since no physical law up to this time has come up with anything resembling a theory of consciousness, where does consciousness come from? Will we ever be able to come up with physical laws that in any way can explain consciousness? Well, there are a group of philosophers who say that we cannot. They loosely have the title of New Mysterians, and here are a random collection of them. I probably missed some of your favorites, but these are philosophers who say there is a limit to what we as human beings are capable of knowing, and we are not capable of understanding our consciousness in any way. It's something that we have to accept. We can explain physical laws, but our consciousness in some way rides on top of these physical laws. They are not religious types at all. They're just saying that consciousness so far has not been explained in any way, and it hasn't been explained in any way because we are incapable of understanding it, incapable of grasping it. For example, in Colin McGinn, in this book that came out in 1999, made this statement here, that consciousness is an extra feature of the universe as basic as space and time and matter themselves. Our fundamental laws that we know today are in terms of time and matter, in terms of fields, but nowhere is there a variable that has to do with consciousness. In axiomatic systems, things like time and space are referred to as the primitives of the axiomatic systems, the undefinable quantities of an axiomatic system. They are the things that you begin with. The axioms tell you how these primitives relate to each other. Points and lines, for example, are primitives in Euclidean geometry. And the first axiom, that between any 2 points there's a line, tells you the relationship between these primitives. And McGinn, I'm still pushing this ahead, sorry, back here. And McGinn is saying that we have to come up with some formulation of the universe in which consciousness is as fundamental an entity as time and space itself. That we'll never be able to explain consciousness in terms of time and space any more than we can explain time in terms of space and consciousness, that they are all independent, and we have to start formulating our laws from the very beginning containing consciousness. Going back to Martin Gardner, Mysterians share a conviction that no philosopher or scientist living today has the foggiest notion of how consciousness emerges, as it surely does from a material brain. These people, these new Mysterians, are not saying that consciousness is something that exists beyond our physical bodies. They believe it's intimately connected with our mental activity in our brain, and that will disappear when our brains disappear. But somehow it's on top of our physical being. And as such, we will not be able to understand it. Here, let me go back to Archimedes and this lifting of the earth. This point here that Archimedes needs to lift the earth from is sometimes referred to as Archimedes' point. It has to be a point outside of the earth in order to lift the earth. And metaphorically, Archimedes' point has come to mean some point outside of an object that you are studying so that you can get an objective view of that object. For example, that was used in the title of this book, Time's Arrow and Archimedes' Point. The author is using the idea that we humans can never step outside of time, so we can never really be objective about time. We're stuck in time, just the way Gödel says we're stuck within the axiomatic system that we're in. And we will never be able to understand time. We have to treat it as a primitive of the universe, something that is there, but that we'll never understand. We have the same problem with consciousness. Where is a point outside our consciousness where we can objectively observe our consciousness? We simply can't step outside of our consciousness. Where would we be if we step outside of our consciousness? And as such, we cannot be objective or really understand our consciousness. All right. To be fair, let me give a few other opinions. This is Solomon Pfefferman, a disciple of Gödel. He probably knows more about Gödel's theorem than anyone around. In a speech, he said, "My own conclusion is that Gödel's theorem is neither here nor there concerning the fundamental laws of physics." So this is, you can see how opposite views are, which means that really any one of us can be an expert on this because the experts themselves disagree. And as far as consciousness, here's a typical physicist view. Murray Gell-Mann, a Nobel Prize-winning physicist, the man who formulated the word quarks, he states the following, typical of physicists: the idea that special physical processes are needed to explain self-awareness, that is, consciousness, will soon die out. He thinks that the present laws of physics, as we understand them, are enough to eventually explain the nature of consciousness. So here again, we have a completely opposite point of view than the new Mysterian point of view, for example. So where does that leave us? Let's go back to the beginning, 14 billion years ago. This picture that somebody took of the Big Bang. Our present creation is that the universe was created some 14 billion years ago, which raises the question, what was happening before the Big Bang? What was going on before the Big Bang? Now, this was a question that was asked some 16 centuries ago, excuse me, here we go, by this man, St. Augustine, in the year 400 AD, roughly. Being a saint and a religious man, he formulated the question a little differently. He said, what was God doing before he made heaven and earth? And in his Confessions, he gives two possible answers. One answer is an admittedly facetious one. He said that God was preparing hell for those who pry too deep. His other possible answer was a bit more serious. He said, I do not know what I do not know. Nescio quod nescio. This almost sounds like a tautology, like it ain't over till it's over, for example. But it's a little deeper than that. To answer I do not know, simply I do not know, to the question, what was going on before the Big Bang, is to imply that the question is a reasonable one, that it has an answer, and that maybe someday we'll come up with the answer. To say I do not know what I do not know implies that the whole question is meaningless. How can you ask what happened before time itself was created? That's the only way we can formulate things, because we are trapped in time. We can't understand. We can ask the question, we can put the words together, but really it has no meaning. And for that reason, we are in the situation that the new Mysterians believe in, that there are some things that we will never know and never really know that we never know. Or you're completely ignorant about some things. So let me end this talk then with St. Augustine pondering away in his chair, just the way I started it with Archimedes pondering away in his chair. Okay, thank you for your attention.